Let's get straight to it. We need to talk about a fundamental shift in systems engineering for operational technology environments. And to be clear, this isn't aspirational. This is about establishing a correct mental model for the operational reality of the systems we're now required to build and maintain.
So, the heart of the issue is a category error. We're all used to deterministic and rule-based systems, right? A deterministic API gives you the same output for the same input every single time. A rule-based system has bounded logic, so when it fails, you can figure out why. But probabilistic pattern engines, and yes, that includes large language models or LLMs, they are fundamentally different. They might be accessed through an API, but they just do not behave like the contract-driven systems we know.
In operational terms, calling an LLM is not like a function call. It's a probabilistic pattern engine. Its outputs are literally sampled from a probability distribution. You can put the same input in and get different outputs out. It isn't executing logic. It's sampling from its model to reproduce patterns that are statistically likely.
And the consequence of this category error is significant. Treating a probabilistic system like a deterministic API is just plain incorrect. In the regulated environments we work in, this kind of error doesn't lead to minor bugs. It leads to systemic, often unrecoverable failures.
So that brings us to the practical impact. Let's really dig into the specific failure modes that pop up when we try to apply our old mental models to this new operational reality, especially in the high-stakes environments we all operate in.
These systems have inherent properties that you absolutely must design for. Outputs are sampled, which introduces non-determinism. That confidence score you see, it's a stylistic artifact. It is not a measure of correctness. The behavior is highly context-sensitive and can change in ways you didn't expect. And here's the critical part. Scale amplifies failures much faster than it amplifies successes, and very often, these failures are completely silent.
This points to a core architectural principle. As soon as that probabilistic system generates an output, the risk has already propagated through the system. Trying to apply governance after the fact is just, well, it's too late. Your control has to be applied before any reasoning process even begins.
And look, this isn't some abstract technical debate. These failure modes create real, unrecoverable audit and delivery risk. For any system that's governed by GXP or the FDA's 21 CFR Part 11 or EU Annex 11, silent automation and untraceable outputs are simply non-compliant. Full stop.
Okay, so given this reality, things like prompt engineering and just chaining tools together are not enough. They're insufficient. The only effective control is architectural. You have to contain the probabilistic behavior inside of deterministic, auditable boundaries.
And this is what that looks like. This is the Operational AI Systems Program Builder, or OASP. Now, it's not an application you go buy, it's an architectural pattern. Its entire purpose is to provide a meta-level control plane that defines authority, enforces a clear separation of concerns, and makes sure that any probabilistic systems are safely contained.
A core principle here is preventing what's called silent mutation. In a lot of traditional systems, state changes can just be overwritten, which makes auditing a nightmare. But here, every single promotion from a generated output to a trusted artifact is append only. History is preserved, not overwritten. That is what makes a system auditable and recoverable by design.
Let's consider a critical subsystem, the Universal Intake and Gating Layer, or UIG. Most failures actually originate at intake. The UIG acts as a containment boundary. It classifies inputs, it gates data for human approval where that's required, and it ensures every single export is an explicit logged artifact. Control has to start at intake.
This kind of architectural shift has a direct and, frankly, unavoidable impact on the role of the engineer. The leverage point for creating value, it's just not where it used to be. The work itself is changing. This slide really illustrates that shift. The implementer's role, which is focused on pure execution, that's becoming commoditized as code generation gets better. The real leverage moves upstream. It moves to the architect who translates intent into constraints, and ultimately to the system owner, who's accountable for the outcomes and the risk. The value is now in the design, the governance, and the judgment. And this right here is the result. You have operator 1, who lacks this structured understanding, and they produce high-variance, unpredictable output. Then you have operator 2, using the exact same tools, but within an architectural framework, and they produce bounded, trustworthy output. The difference is not the tool. The difference is the operator's mental model and the system's design. So, let's just state this plainly. The job has changed. It is no longer sufficient to just be fluent in a framework or an API.
The work now is operating the abstraction layers, the intake, the governance, the promotion, that contain all that probabilistic behavior and actually make the underlying tools safe for operational use.
Which brings us to a final and critical conclusion. This isn't some advanced topic. It's not an optional specialization. This is the new professional baseline for the work we do. Without understanding these abstraction layers and control points, the work cannot be delivered safely or at scale. And this is true regardless of the vendor, the platform, or the tooling you're using. The constraint is conceptual, not technical.
Therefore, systems literacy in this domain is now a foundational capability. It's a prerequisite for effective engineering in any regulated environment that plans to use these technologies for any kind of non-trivial work. It's not aspirational, it is required.
The system is not autonomous. It's a tool, but the job of the engineer operating that tool has fundamentally changed. The work isn't about tool selection anymore. It's about operating those tools safely within a governed architecture. So the question is, are you prepared for that work?